I'm Abby Phillips, and this is my second video from positioning in the RDS net protocol. So first, I'm going to start off with pulmonary blood flow. So this process begins when deoxygenated blood from the body is received by the right atrium, flows into the right ventricle, and then is pumped into the pulmonary trunk. The pulmonary trunk carries the deoxygenated blood into the lungs um, through the right and left pulmonary arteries in the lungs. The blood is oxygenated and then will flow back to the heart. Then it'll go through the left atrium, through the right left ventricle, and then through aorta. Gravity affects pulmonary blood flow through the hydrostatic pressure difference between the top and bottom of the pulmonary arterial system. At the uppermost part of the lung, the pressure within the vessels may be less than the alveolar pressure. Right. Then I'm going to go over pulmonary vascular resistance. So pulmonary vascular resistance is the measurement of resistance to the blood flow in the arteries that supply blood to the lungs. If the pressure in the pulmonary vascular is high, the right ventricle must work harder to move the blood forward past the pulmonic valve. Pulmonary vascular resistance is like systemic vascular resistance, which refers to the arteries that supply blood to the rest of the body. The normal value for pulmonary vascular resistance is 0.25 to 1.6 millimeters of mercury. And then also here is the calculation for it. So Pacelli's law, excuse me, describes the relationship between the flow rate of a fluid through a cylindrical vessel and the factors such as pressure difference, vessel diameter, and fluid viscosity. And then here's also the calculation for that right here. Right, and then we're going to go over the zones. So there's zone 1, 2, and 3. The lower you get, the more blood flow. As you can see through each zone. So the alveolar pressure is greater than the arterial pressure and the venous pressure. And then right here, the alveolar pressure is greater than the or the arterial pressure is greater than the alveolar pressure and the venous pressure. And then in zone 3, the arterial pressure is greater than the venous pressure and the alveolar pressure. So yeah. Okay, so cardiac output. We're just going to talk about cardiac output and how it affects ventricular preload, afterload, and myocardial contractility. So an increased preload generally boosts your cardiac output by enhancing stroke volume, while higher afterload can reduce it by increasing resistance. So enhanced myocardial contractility improves cardiac output by allowing the heart to pump more forcefully. Ventricular preload refers to the degree of stretch in the ventricular muscle fibers at the end of diastole, just before the heart contracts. It is primarily determined by the volume of blood returning to the heart and filling the ventricles, which that influences the force of contraction. So myocardial contractility refers to the ability of the heart muscle to contract and generate force independently of preload and afterload. As well, it is influenced by factors such as calcium availability, certain medications, sympathetic nervous system activity, with increased contractility, enhancing the heart's pumping efficiency and stroke volume. All right, and that just covers pulmonary blood flow and how gravity affects the lungs. So, bottom of your lungs has the most blood flow.